Yes, welcome to our paper. This paper is a collaborative effort between the Will Lab of Tongji University and Thyssen U2 Lab, and has been accepted by CVPR. It aims to design a masking strategy for adaptive online localization of noisy samples, so as to elevate overfitting of the model to noisy samples. And first, we observe in our experiments by visualizing the activation map results that the model trained with a completely clean dataset still focus on the foreground region of the image and the center of the target for the incorrectly predicted samples, while the activation map for the incorrectly predicted samples for the model trained with a noisy dataset focus on some background region, such as the corners of the image. The activation map of the samples correctly predicted by the model focus on the edge of the foreground target, because the feature map of these samples are negatively disturbed by the noisy samples and thus cannot focus on the center of the target. Thus, motivated by this, our designed adversarial masking strategy first finds the image region that the model focused most on during the current training strategy. Based on the activation map, and then generates a mask with random values centered on this region to make the model focus on the remaining regions again. However, we believe that setting the same mask strategy or a random mask strategy for all the samples is not sufficient for targeting the model for localization. Specifically, we compared a fixed mask size, a noise-independent mask strategy with a random mask size, and a noise-aware mask strategy with a larger mask ratio for noise samples. The results of the strategy, as shown in the figure 2, show that noise-aware masking strategy exhibits better experimental results, and thus this drives us to design a method for adaptive localization for noise samples. Briefly speaking, we generate mask ratios with the help of a Gaussian mixture model, which is a more commonly used in the field of noise label learning, so as to target different mask strategies on clean and noisy samples. In addition, inspired by the MAE model, we introduced a self-supervised image reconstruction module, which introduces noise-free self-supervised signals by reconstructing the masked images to improve the generalization ability of the model. This is a self-supervised adversarial noisy mask framework (SAM) designed in our paper. The overall framework contains 3 main modules: adversarial mask generation and noisy label localization, and the self-supervised mask reconstruction. Since our model is a localization strategy, it can be combined with existing methods to improve their robustness to noisy samples. For the adversarial noisy masking module, first the sample is input to the network to get the prediction results and feature map, and the activation map is generated according to the category with the largest prediction value. And the point with the largest activation value in the map is selected, which represents the area that the current model pays most attention to the sample. For the noise samples, these areas are often discrimination irrelevant areas, such as background, so we need to set a larger mask ratio so that the model can extract the correct category-related information from the remaining areas of the image. While for the correctly labeled samples, the activation map is shifted to the edge areas due to the influence of noise samples. So we set a smaller ratio so that the model can generate activation map results with completely coverage of the foreground. Specifically, the size of the masked region is generated based on the cross-entropy loss and the given noise labels by the weight of the Gaussian mixture model, which is denoted as I. For the aspect ratio of the masked region, we choose to sample it from a uniform distribution, and finally we assign a random value to the chosen region. Moreover, for the masked region, we consider that it may belong to any category, so we subtract the mask ratio from the largest prediction value and increase the values for all categories. And the model calculates the cross-entropy loss with the regularized labels. Finally, for the masked image, we input this feature map into the decoder to reconstruct the masked region, and for the samples with a large mask ratio, which are more likely to be the noise samples, their self-supervised reconstruction loss is larger, so it can more effectively elevate the overfitting. So the overall objective function can be summarized in this form. On the left is a pseudo code flow of the method, it can be seen that our methods are not limited to a specific framework and can be flexibly combined with existing methods. For the experimental part, we conducted experiments on the Cypher 10100 simulated noise settings and the real-world noisy closed 1M dataset. Table 1 shows the result of our methods in the symmetric noise setting. Our method can achieve a very significant performance improvement on the corresponding benchmark methods when combined with dynamics and C2D, especially in the high noise cases. And our method can achieve a more significant advantage over other existing methods. This is the ablation experimental result of our method. We can see that the adversarial noise mask generation can bring the most significant performance improvement, while the noise level regularization and self-supervised mask reconstruction module can also have a slight performance improvement to the method. And we also compare the online and offline mask generation approach. As shown in the figure 4, our online strategy is superior to the offline generation ones. And we further combine SM with existing noise level learning methods, including the common cross-entropy loss, co-teaching, CDR, and ER+, and we can see that our method have a very significant performance improvement for these methods. And this is the result on another real-world dataset, Animal 10M, and we also verify the effectiveness of the motivation on closed 1M. And that's all we worked on. Thanks for watching, and our code will be open sourced at the following GitHub link, so feel free to follow along.